making science easier and getting meaningful results into scientists and policymakers' hands. Rhydwyn, ladies and gentlemen.
Thanks. As I said, fast, beautiful, and easy Bayesian modeling. Can we have it all? Who am I? I'm Rhydwyn. I'm a medical statistician working in public health. This means that while I have some computer science in my background, almost everyone that I work with doesn't. We train scripting in data languages on the job, and we don't do it that well. And so that's going to come into my talk. I'm not working with people who do end-to-end well-tested systems. Unit testing is a great idea, and I look forward to it. We have, where I work, we do open data. We're providing data on the New South Wales health system to a whole range of customers, and often they want data which is about rare diseases or rare events and about small populations. So the kind of people will get someone who's working in a community group or a charity who wants to know about the kind of cancer that they work with, but that it might not be a very common cancer. And if they want to break down over local government areas, you might be talking about some local government areas having a handful of cases a year. A lot of people get cancer, but once you're starting to talk about small cell lung cancer, which is the way that researchers, that policymakers, that journalists want to think about, that can be a really small number. So you get a lot of variation. We make our data publicly available through maps like this. So this is the endpoint. Nice, easy to understand, at a glance stuff. What do I mean by fast? We do a lot of those maps. We have a 2-weekly release cycle, and in that we might push 30 diseases or hospitalizations or whatever we're thinking about. We'll do that broken down by sex, by age groups, by other demographics like Aboriginality or country of birth. And we're building a map for every one of those. If we're looking at a 25-minute build time for one of these models, that can mean that we're looking at a couple of days just to get the data prepared, which runs everything else down to a halt. There are obviously other options, but again, I'm working with statistical analysts. I'm not working with programmers. Things like Hadoop are great, but it's an extra level of understanding. It's a lot of extra training to get people who are not used to thinking about things like networks into a position where you need to think about, I might not have access to my hard drive, the network might go down. So it's good to do it all in-house. We've got a local data server which is quite powerful, but it can be not really powerful enough. We want it to be easy. They're not programmers. I don't want to be teaching advanced programming topics. It's a waste of my time, it's a waste of their time. We want this to be accessible. We want them to be able to do what they can do, which is be good statisticians, not deep coders. And I like code that's beautiful. I don't want to look at something that's ugly all day. I don't want the syntax to fight me. I don't want to have to struggle to understand what I'm looking at. Here's a classic example. You'll find this in a lot of textbooks about the problems we have. So kidney cancer death rates can tell us some really important things. It might be about how late you're being diagnosed. It might be about what your access to care is like. But if we look at the highest and lowest cancer rates, they look fairly similar. And if you know anything about the geography of the US, you might see what the similarity is. Population density looks like this. All those high and low rates were small number issues. They were low and high because it might be that only 5 people in that county had kidney cancer. So the difference between 2 of them dying and 3 of them dying is huge. This isn't great. This, again, we're working with journalists, we're working with politicians, we're working with policymakers. They get headlines, they get raked over the coals over a 20% increase in the cancer rate deaths. We need to be providing them better options than that so that they can come back and say, yeah, no, look, it's a 20% jump, but it's not really a 20% jump. It's a one-person jump. Here's an example in baseball. This graph is great. You've got a really good sign of variance. And I hope that no one would look at this and say, hey, that guy by the first red line right up there, that's the batter I want. That's the best performer of this year. Like, hire that guy. It's beginner's luck. We know this, but we want to wrap this up in a model. This is pycon-au. I don't want to talk to you about baseball. Let's talk about cricket. Right. So when I played cricket as a kid, I loved hitting over the fence. Whole lot of reasons, got to annoy the neighbours, pretty sweet, definite bragging rights. So let's measure this that way. The rate of hitting sixes. I'm going to call the best Australian cricketer the guy who hit the most sixes. I'm going to go for tests, days, and 2020 first class, international. So here's what that data looks like. Again, now the interesting thing is that the baseballs was much larger than this. So what we've got a whole bunch of people who never hit sixes. Now, a lot of those are going to be primarily bowlers, or they're going to be people who don't have that aggressive playing style. Some of them might be very good. I was told at dinner last night that Don Bradman got only 6 sixes in his entire career. I'm not going to stand here and say he was a crap player, but he wasn't very good at getting sixes. So, as we said in the last one, who's our best player? Who's that guy that's right up there, fucking brilliant at hitting sixes? Sorry. Chris Lynn. Show of hands, who's heard of Chris Lynn? More than none of you. You're doing better than me. Now, this guy is pretty good at hitting sixes. He's fairly young. He only plays 2020, and 2020 is a game where that's useful. So maybe he is. But I'm still nervous. I'm still interested in this guy. I think he might be our guy. He's got a lot more experience. We can be a lot more sure. That's Chris Lynn. How are we going to do this? We're going to use what's called a shrinkage estimator. We're going to use a bit of information from the player's individual score, that's the rate that we saw in the first graph, and we're going to use a bit of information from the team's score, that is the average information. And we're going to trust, because basically we've got 2 things going on here. We've got actual talent, your ability to hit sixes in a kind of long-term way, and we've got some luck, and we've got a lot of beginner's luck in those people that we don't have a whole lot of data for. So we're going to trust people are really talented more if we've got more data for them. So now I'm going to talk about defining the problem space in a Pythonic way. So people who know me know that I do most of my work in R. I'm a big fan of R. We can have those fights later. Notable mentions, RPy exists. There are lots of great libraries in R that do Bayesian modelling. They're out of scope. There's lots of good things about them, but that's cheating. We could do a whole day on Bayesian modelling in R. We are going to look at PyStan, excuse me, which is an independent library written in C++, bindings into lots of things, and we're going to talk about PyMC, which is a pure Python. Why PyStan? Hamiltonian Monte Carlo with a no U-turn sampler is really cool and really fast, and it's got a really low memory footprint compared to a lot of other options. This means you can fit bigger models than you would otherwise have been able to do. Heavily tempated C++, as I said, good performance. Lots of interfaces. Your models are written in specific Stan syntax, and then you run them using an execute in Python that exposes all the data to Python, and then you can work with the data in Python. Same for your other things. So you can actually move these models around, which might be useful if you're not sure where you're going to end up from a modelling perspective. Let's start with a pooled model. So basically what we're going to do for our first attempt is we're going to say there's no such thing as talent. Every cricketer is as good as every other cricketer at hitting sixes. Everything about those differences, the ones who have a lot of sixes, the ones who have no sixes, that's all luck. Don't care, we're just looking at the centre value. So we're matching sixes as a binomial distribution on the numbers of balls you've faced, and theta, which is the group mean, the group talent. And that's always going to be 0 and 1. It's got a really simple understanding. It's just the rate of hitting sixes on balls faced. For a reminder on binomial data, it's a series of independent events. It's the model that you'd use for flipping coins or rolling dices, anything like that. Really nice and simple. The mean is just your rate of hitting sixes by the numbers of balls you faced. You've got a rate of 0.1 and you faced 100 balls, then we'd expect you to get about 10 sixes. The variance is n theta by 1 minus theta. So the closer you are to 50%, the closer your rate is to the middle, the larger the variance. So the more, if someone's hitting around 50%, then we'd expect them to get more different numbers over a bunch of trials than someone who's got a 1% chance. This is the Stan syntax. Whether or not you like it is a matter of taste. I really like it. I think for mathematicians, for statisticians, if you're dealing with people like that, it's really quite intuitive. It looks a lot like the kind of maths that you're used to doing, and that's on purpose. We have data where we're defining the number of players we have, the number of balls they've faced, that's a vector because every player's faced a different number of balls, and the number of sixes that that player hit. We've got a parameter, theta, that's our ability to hit balls, our ability to hit sixes, sorry. We're giving theta a fairly uninformative prior. That biases us towards the middle, but not very strongly. Basically, all we're doing is cutting down the search space and just saying, look, it's going to be around there. And we're setting up the likelihood, as we saw on the last slide. In Python, it looks like this. We just set up some data, run fitbin. The model code here I've just put in as a string. You can also just call it as a file on disk. 10,000 iterations for 4 chains. So that's just how long I want it to run, and I want it to do that on 4 processes. Stan is multi-threaded, so upping your number of chains is a good way to increase your sampling. It's really trivially parallelizable. We extract the data fairly easily, and if we've got matplotlib installed, we can get really nice plots just through the plot functions. You may be wondering why I'm saying plot for eta and mu. That is a mistake. That is our next model. We'll have those. We should have a plot theta there. This is what happens when you write slides at the last minute. One thing that I didn't want to do was spend all my time telling you about a model that you could fit in stats models in 5 minutes in an entirely frequentist framework. So let's actually talk about that shrinkage model. Let's have a look at how we do when we want to have a more complex model and a model which is a reason that we'd go to Bayesian analysis. So now, first line looks very similar, but we've picked up some underscores. Because every player now has their own sixes, their own balls, as they did before, but also their own theta. They have their own parameter. They have a level of talent, but these talents aren't completely independent. The talents are forced to centre around and come in towards the general population's theta, which is mu in this one. Now, there's an inverse logit out the front of our theta. This is, if you've ever done logistic regression, all we're doing here is setting up a logistic regression, which means that we're taking numbers that can occur anywhere on the real line and we're mapping them into 0, 1 so that we've got a nice, so that we've always got a valid value. Here's the logit function. So in Stan, we set up very similarly. We've got data, which is exactly the same. We've got now 2 parameters. We've got mu, which is our group's mean, and we've got eta, which is a vector of length n. That's going to be the offset, which is the player's personal talent. We've got a new thing. Transform parameters. Theta is now defined. This is just the logit function of of the group mean and the individual mean. So that's how we're doing the shrinkage estimator. Then in the model, we set up priors, again, minimally informative priors. We're only saying these numbers are reasonable. Outside this search space, we're probably not going to do much. And for each player, we have their own model. We run that, we get a really nice posterior on mu, and we get a posterior for each of the etas. And if we look at this, we have kind of 2 groups. One of them doesn't appear to converge very well. You've got a big variance there. That one, those are the people with 0 sixes. It's really hard to say something about the quality of a player if you have no sixes. If a player's faced 100 balls, got none, are they an unlucky 1 in 100? Are they a 1 in 10,000? Are they a 1 in never? We don't know. So that's why we've got that separation. Stan's got a lot of good press. A lot of statisticians are interested in it in the moment. Why wouldn't you use it? You're calling out something outside of Python. You get a lot of info on the terminal, but it's a bit of a black box. You've got less control than you would in something that's pure Python. There's also testing. And they do, in their manuals, there's a bit of a, look, we know we don't have a full testing framework, but Probably you want a bit more than that, and they don't. PyMC3. PyMC3 is a complete rewrite of PyMC2. It's got a new syntax, which I really like. I think is, again, quite beautiful. I wasn't a fan of the PyMC2 syntax. It's currently in beta, but there's a lot of work going on it. It uses a no U-term sampler and Hamiltonian Monte Carlo. The developers have specifically said we were inspired by the STAN project and wanted to be able to use some of these newer fitters to in the PyMC, and we found that we needed to do a full rewrite because it makes a lot of use of gradient methods that aren't really possible to retrofit. It also does optimal starting position, so you get a really good, you can ask it to give you a good guess of your starting position, and that can cut down your time to convergence by a lot. This is what it looks like. You do everything in the context manager. Again, we're defining theta with a prior. We're using a beta as we did in our, this is just the pooled model. We're not going to go into the hierarchical model for PyMC. You define your likelihood as y. This start, find, map, that's their optimizer. It performs quite well. I'm using a Metropolis optimizer here, but you could also use a no U-turns, or they have a whole range of optimizers, which is a good thing. In STAN uses really good optimizers, but you've only got one of them, so if it turns out that your problem doesn't perform well, you're stuffed. This one, you can pull out a whole bunch, and so there's probably something in there that will work well for your problem. Fit the model, get the trace plots, get all your data out. Excellent. We've got good convergence, we've got very similar results. Final thoughts. This modelling is hard, there's a lot of pitfalls. Do build your model with dummy data, make sure that it gives you the right answers there, then move on to starting to look at your problem. What would I use personally at the moment? I'd still go with STAN. PyMC3 looks really good, but it is in active development. It's still in beta. STAN's been around for a couple of years. It's what I'd use for production. In a year or two, I'd probably be making a different call. I'm really excited about where PyMC is going. Thanks.
Any questions?
Thank you for this. Can you remind us again why you didn't do it in R? Is it because it's Pycon?
Basically, yeah. That seems... when I started this project, these were things that we were looking at work. We ended up going in a different direction, and we're using a spatial smoother on a Markov random field, and we're doing that in R. So...
R?
R is a statistical programming language that it basically sits between a sort of standard programming language and a stats package. So you can do a lot of the things that you can do with a statistical package, but you can also do things like access network servers, do web scraping. So it's much more full-featured than a sort of specific statistical package like you might have with Stata.
So working with some other things like random forests or neural networks, a critical stage is essentially data pre-processing, things like normalization or handling missing data, etc. Bayesian models potentially more robust to some of those issues, or is that still a big deal?
It depends on the specific model, but many Bayesian models are like a specific reason that you would use Bayesian modelling sometimes is because it's robust to missing data. Now you need to get your models right to do that. For scaling their normalisation, generally you won't need to normalise for model convergence, but you might normalise for efficiency. There are some things which will converge faster with normalised models, but will still work with non-normalised.
Hi, just got a comment since there's no questions at the moment. Just there's sort of two books sort of talking about Bayesian stuff and Python that are quite good. One's called Think Bayes, and it's Creative Commons license as well as being viable by a guy called Alan Downey, which is sort of much more kind of taking you through it from sort of first principles, kind of a really basic one. And then there's an IPython notebook book called Probabilistic Programming and Bayesian Methods for Hackers. That's an IPython notebook, and he's using PyMC. I'm not sure if it's version 2 or 3, but I just thought I'd put that out there.
Great, thanks.
Any more?
Out of curiosity, how big are the data sets that you're running through this, and do you find do you find limitations and differences within Python and R when you start hitting large numbers?
So the data sets I'm working with here are reasonably small. I could get information on 424 cricketers, so that's what I've been working with. Yeah. I'm sure you can find information on that. I have friends who do very large Bayesian data sets in both R and Python, so I know it's possible, but I can't comment on efficiency.
Have you ever, because that was something that we hit in Mozilla, was when we started to get to the really large numbers, like the hundreds of thousands of comments that we were trying to work through. And somebody, like one of our team, really started looking into Java for that, because we just started hitting, I don't know, issues. Maybe it was also our limitation of understanding the languages as well, but yeah.
Yeah, I haven't looked at Bayesian modelling in Java, although, again, Stan is in C++. I would be tempted to look at that as an option.
We probably have time for one more.
This, I guess, more of a general question, like about one of your earlier comments about unit testing. I also have the same difficulty trying to convince people that it's something that you really should do. I was just wondering what stuff you've maybe tried to convince your people in your team or the people you work with to test stuff out, or some ideas that you've had, because the thing that comes to my mind is, particularly with the talk early this morning, it's often high stakes data, and it's just not really acceptable that there's, looks like it works, and then particularly in organisations like you work for, that data is going to a policymaker, and there's big consequences. So
one of the things we've been doing is building some internal. We've got a mix of people who are more programmers and people who are more analysts, and having the people who are more on the programmer side build some general test frameworks. We have a fairly consistent things that our data looks like, things that our database looks like, basically to take some weight off, so that we say, look, you don't need to please come and learn about testing. But if you don't want to, you don't understand it, we can just put this last line here. You just need to put in these values and it will do its thing, and come find us if it doesn't work. So we're trying to take some of the load off the analysts to things they're not really interested in doing. I guess as an alternative to trying to skill them up, but it would be good to have more ability to skill up.
I'm just wondering about a bias in this, and how the lack of data influences bias of the results in, say, comparison with random forest.
So Bayesian models can be biased. They can be biased by their priors, but that goes down as the data gets larger. And 424, it's not big data, but it's big enough to kind of be walking away from that, to be walking back from that bias, particularly when you're not putting strong priors on. Because you're explicitly defining a model, while you can still run into the issue of overfitting, you've got a lot less risk of overfitting, because you're not just saying, do the best you can, which will tend to overfit. You're actually saying, look, this is what it looks like. Make the model, make the data fit that as best you can, so you can control bias from that side as well. But I think you'd need to be much more domain specific if you actually wanted which will give me less bias.
Okay. Yeah. No, the question probably, for me, probably stems from the fact that a lot of the stuff that you're doing, or I'm just surmising, a lot of the stuff that you're doing is for policymakers. So therefore, was it your team, or was it policymakers who set the sort functions that you actually use?
We tend to set them, but my team has a lot of well, I'm a medical statistician. We have other medical statisticians. We are aware of the area, and even if we don't know much about that particular cancer, we are deeply involved in the ways. And I mean, we are intentionally biasing it. If you think about the best measure, the unbiased measure of a player's performance is their straight performance. We are intentionally biasing towards the mean because we believe that is a better number. And again, in the kind of state data, we are intentionally biasing small groups or small areas towards the mean because we believe that is a better estimate than the raw estimate.
Thank you.
Righty. Thank you, Rhydwyn. And as a memento of appreciation, we have this thank you mug from PyCon. Okay, guys, lunch should be served, so help yourselves.